Wait, so you need another way of doing stoichiometry? Really? Okay, I've got something for you, but comes with a couple of warnings. So we will talk about another option for doing mass-mass stoichiometry. And one of the things I really like about this method is that once you start using it, it has a real logical flow to it. There's certain things that just simply make sense as you're doing it. Well, the obvious question is, why wouldn't I have shown you that the first time? And it comes down to the answer of what don't I like about it. And once we move into solutions or gases where we're not talking about mass and mass stoichiometry, starting with a mass, finishing with a mass, then that logical flow really disappears, and you're going to have to do either a couple of steps, additional steps at the beginning, or a couple additional steps at the end in order to either get a mass to start with or turn your mass that you finish with into the thing that you're actually looking for, because this really only works well for masses, starting with masses and finishing with masses. However, we'll go through it. So here's a typical stoichiometry question where we start with a mass of known and we're asked to calculate a mass of some unknown. Now what we've done so far is two different ways of doing stoichiometry. One is with three distinct steps, where in the first step we take the mass of known and we convert it into moles of known, and in this case that would be dividing the mass of hydrogen by the molar mass of hydrogen, turning that into a number of moles. And then we would take that number of moles that we know, the thing that we're calling the known, the hydrogen, converting that into the moles of the thing that we're looking for, the unknown, using the molar ratios or the balancing coefficients from the balanced chemical equation, which I quite often talk about as the recipe in that reaction. And then finally, once I have the number of moles of ammonia, in this case NH3, I use that number of moles and the molar mass to calculate the number of grams, or the mass of ammonia, that I need in my question. And I'll get out of the way. Okay, the other option that we have, and the one that I kind of prefer because it works all the time, and the only downside is we have to really look carefully at the units, but that is not a downside, is what's known as the factor label method, where we go through the thing. We start out with our mass of known, the 32 grams of hydrogen. We convert that to moles of hydrogen using a conversion ratio. And then we convert that to moles of ammonia using another conversion ratio. And then finally we convert that to mass of ammonia using yet another conversion ratio. And all of the arithmetic, all of the calculations that we're doing in both of those options are exactly the same. The only difference is how it looks and perhaps the order in which we do things, but even not really that, because if I look at the three distinct steps that I did a moment ago, I'm doing the factors, the converting factors, in the same order. And I would end up with exactly the same answer, 181.33-ish grams of ammonia. Okay, what is the third option? And again, pick a method of stoichiometry that works. And the only reason you would be watching this is if the previous two really aren't working out for you. But what you're going to be doing is starting with masses, which is kind of where we need to start anyhow. But if you look at a chemical reaction, we know that those balancing coefficients represent numbers of moles or numbers of particles. We always thought of it in terms of numbers of atoms and molecules, so we want to say 1 molecule of nitrogen reacts with 3 molecules of hydrogen to make 2 molecules of ammonia. But I need to be thinking about that in terms of moles. 1 mole of nitrogen reacts with 3 moles of hydrogen to make 2 moles of ammonia. The problem is, what I want to work with is grams. So how do I do that? I got 32 grams. I need to find the mass of ammonia. So what I'm going to do is I'm actually going to take those molar amounts and turn those into mass amounts. So instead of 3 moles of hydrogen, how much mass does that have? Well, hydrogen has a mass of 2 grams per mole, so 3 times that. Ammonia has a molar mass of 17, so 2 times that. And then what I would have is I would have that reaction written in terms of masses. So 6 grams of hydrogen would make 34 grams of ammonia. Exactly the same reaction, exactly the same balancing coefficients. It's just now, instead of talking about numbers of particles or numbers of moles, that tells me mass. Then what I want to do is I want to take the thing that I'm looking for and the thing that I have and set up a ratio. So now 32 grams of hydrogen over the 6 grams of hydrogen is equal to the unknown amount over the 34 4 grams. And it becomes really, really important that you know which order things go in terms of which one goes on top, which one goes on the bottom. So that's probably one of the biggest challenges of this version of doing stoichiometry. And you end up with, no surprise, the exact same number that we've had twice previous, because we'll be doing all of the exact same calculations. This just changes the order. If I were to take a different one, just to kind of look at something different, here I've got 4 ammonias, 7 oxygens, making 4 nitrogen dioxides and 6 waters. All I really care about here is the oxygen and the water, so I can kind of ignore everything else. So I take the reaction that I have. I'm looking for oxygen, I have water. I turn my balanced chemical reaction into a masses instead of numbers, instead of molar numbers, molar amounts. So oxygen has a molar mass of 32, water has a molar mass of 18, multiply those by the balancing coefficients, so now I've got that reaction written in terms of masses. Set up the ratio. If 224 grams of oxygen will be enough to produce 108 grams of water, how much oxygen is needed to produce 75 grams? Solve the ratio, Bob's your uncle, 155.6 grams of oxygen. That's all there is to it. Now you might be looking at that and thinking that is really awesome, and it is. However, 2 things. You're just doing stoichiometry. It's the same stuff, same calculations that we've done before. It's just written in a different order. And 2, there are some things about bad news. There are some bad news statements. And one of those is there is no shortcut. There is no this is obvious. There is no this is easy. There is no do exactly the same thing every single time and the answer will just magically fall into your lap. There is not one of those. 2, if you're trying to do one and you're getting it, I would honestly tell you to stick with it. But if the 2 methods that we did beforehand didn't work for you at all, maybe this one will. But then there's the real problem with once we start moving into solutions or gases stoichiometry, this method really does not work at all. I shouldn't say it doesn't work at all. It's not very efficient though. You will have to do extra steps to take something that's not a mass and turn it into a mass, or take something that is a mass and turn into something that's not a mass, because if you're not dealing with start with a mass, finish with a mass stoichiometry, this method is going to be a nuisance. So maybe by that point you'll be such a stoichiometry hero that you can pick up one of the other methods much more easily. Until then, we'll talk to you another time.